Hi, welcome to my channel, Math in Local Languages, and so Mathematics in Local Languages. As you know, this channel normally is made for teaching mathematics in my local language, which is Lingala. But today I'm gonna do a little bit of an exception because I am going to solve an exercise that was sent to me by some of my friends who are English speaking individual, so I cannot make the video in Lingala. So we are going to solve an exercise of functional analysis. So just let us start. So here is then the exercise. The exercise is about, let me arrange my screen. Yes, here it is. So we are we we are given two Banach spaces, the L2 spaces, and the space of continuous function on the interval 0, 1. And in application, an operator, we can say, because we're going to say that we cannot call it an operator. And sorry, I need something. And an operator T from L2 to C0, which is such that if you have an L2 function small f, it will transform it to a continuous function, tf, which is defined by this formula. Tf of x is given by the integral from 0 to x of tf of t dt for all x in the interval 0, 1. So here we are assuming that this tf as defined here is going to be a continuous function. We can prove it because this is the question that we are going to solve in the first part of the exercise. We can prove it, or we can just assume that yes, it is continuous, and then we will see. But here I'm going to prove it, but I'm not going to give like I'm not going to give like a complete proof. I'm going to say words that will help one to see why this TF as defined here is continuous. And we're going to concentrate more on showing that T is a bounded operator. And the second one is gonna solve. We're gonna solve this question, that is to compute the operator norm of our operator, the operator T, and we're gonna show that T is a compact operator. Let us then get started by in the proof of in the proof with the proof. So the first part is to prove that I'm sorry. I have to zoom. Yes. Let me do this. I don't like this kind of stuff. Okay, let us just ignore it. So the first question that we're gonna solve is to show that T is a bounded operator. Remember, this T is first of all an operator from this space. Let me pick another. Uh, is first of all an operator from this space to this space. So to show that it is a bounded operator, first of all, we have to prove that it is a well-defined operator. And we have to prove that it is linear. We'll have to prove that it is also continuous. That is what it means by being bounded operator. Then we have three things to prove in principle here in this question. When we want to prove that this operator T, defined from this space to this space, is bounded, we need to prove three things. First, T is well defined. Second, T is linear. Third, T is continuous. The first and the second is the second thing to prove is very easy. The third also is gonna be easy as gonna see. The first can be somehow people don't really care about the first point of an operator. They don't care about it because they think that it is already, yes, it is an operator because they said it. They say. But we have some. Let's see. How is it well defined? Because like TF as given here, uh, if you have another representation of F, so you have F that can be written in a certain way, and another F. So you can write F in two different way, right? F in two different way, for example. We don't know how you're gonna do it, but you can write F like F1 and F2, for example, like this. If they are equal, but so it's like the F can be written as F1, F can be also written as F2, but we cannot, because of that, have TF1 different from TF2. Just because F has been written in two different ways, F1, F2, and we see that for this representation of F, TF gives you another answer, and for the other representation of F, TF gives you another answer. Then your application is not gonna be well defined. This operator is not gonna be well defined. But for us, this is not gonna happen. Why? Because the integral is well defined. T is basically defined with respect to this formula. So uh, because the integral is well defined, so this situation is not going to happen to us. We know that this application is well defined. Now, we don't only need to show that it is well defined, we also need to show that it is continuous. Now it is continuous. Why? Because this TF must belong to this set. Then we have to prove that it is continuous. So then we have to prove that TF is that means this formula gives you a formula of a continuous function. This can be also seen. Why? Because this function is integrable. This function is integrable. The function here, y, f is in L2. F is in L2, then f is integrable, is in L1 also. So we know that L2 of 0, 1 is a part of L1 of 0, 1. Why? Because 0, 1 is bounded. Since 0, 1 is bounded, then L2 of 0, 1 is a part of L1 of 0, 1. Therefore, f is integrable. F is integrable. The function which associates t for each t is also continuous function, then it is integrable on this interval. So you have a product of two integrable function. It is also, so even this function t is in L2. Therefore, the product here of two L2 function is an L1 function. So this function is integrable. This function is integrable. Therefore, we know by the fundamental theorem of calculus that if you define a function like that for an integrable function, this function is going to be continuous. So this function here defined is continuous. This is our df. Then tf is continuous. So in this way, we make sure that t is in fact an operator defined from this L2 space to the continuous set. So we have to go and show that it is now a bounded operator. That means it is linear and continuous. For that, first let us show that t is linear. So to see that t is linear, what we're gonna do is uh, let now take f and the g, the element of the space L2, and take two real number, two constants in the set of real number. We have to prove that t of alpha f plus beta g is alpha t of f plus beta t of g. This is very easy to see. Why? Because the integral is linear. So when we will put alpha f plus beta alpha f plus beta g, Here, instead of f, so let us do it just quickly. T of alpha f plus beta g applied at x will be equal to the integral from 0 to x of t times alpha f plus beta g of x dx. This is by definition of t, but then we can distribute to have this alpha t f of x plus beta integral from 0 to x t g of x dx. Oh, I'm sorry. So this is g of t, d of t, d of t. I should have t here. So I don't need this one. Let me write it properly. Yeah, so I have this one. You see that the first one gives you the formula of tf of x plus the second one gives you the formula alpha t g alpha tg of x. But then this is by definition what we call tf plus beta tg applied at x. So therefore, because we have this for our x, we can conclude that tl plus beta g is equal to alpha tf plus beta tg. This proves that your t is a linear operator. So now we have to prove that t is bounded. For that, we have to show that. So what we need to show for that? So we need to show that there is a real number that we can call, I don't know, r, such that for all for all f in L2 of this one, what we have is, if I compute the norm of TF in this form, in this space, I will have that this is less or equal to this constant that I have to identify, r times the norm of f in the L2 in the L2. So how can you interpret this one? It means that to prove that a linear operator, as we have proven t to be, to prove that a linear operator is bounded, you only need to show that there is a real number that you can call r, such that for any element f in the domain of their operator, the L2 norm, the norm of your operator applied to, or the norm of the image of that element in the arrival space is less or equal to that constant, to the constant that you have to identify, times the norm of your f in the source space. So here we have our source space is this one, and this is like where the arrival space. So this is what we have to show. So now we have to identify something like that. The strategy to do it is you try to compute this norm. We try to compute this one. The strategy to identify this value is you try to compute this one and see if in the computation you are going to see a constant appearing somewhere being multiplied by the norm of your function, the function that you started with. So then one needs to know what is this one, L2. We know that it is this one, the integral from 0 to 1 of f of t squared dt to the power 1/2. So we have to compute this one and see a quantity like this appearing in our computation with a constant that we will identify, which will be our R. This is the strategy. Let me put it there. This is the strategy how to do it. And one also must know how to compute this norm. This norm TF must know what is this one. C0 of we have to know what is this. This is the soup of what? Of the absolute value of TF of x by definition when x is in the interval 0, 1. So this is the norm. So one needs to compute this one and see how it will, from the computation of this quantity, how we can make this the quantity, the first quantity here to appear. So let me say it again. I'm sorry, the video is gonna be long. One need to compute this, and from the computation that one will be doing, one will need to see this quantity appearing, so with a constant that one must identify. So this is like the aim that we our aim. So then let us compute it. But we can easily see that to compute this quantity, which is the supremum, like the the biggest value of the set, one need also to estimate, or to estimate the value, the element of the set. So to know the biggest value, we may be it may be interesting, sorry, to also know the behavior of the element of that set. So for that, we take x in this interval. We then estimate what would this one give us. This will give us the absolute value of the integral from 0 to x of t, f of t. But we all know that the absolute value of the integral is less or equal to the integral of the absolute value. We have this one, so this will give us this dt. Then we can remember something that is called the order inequality. The order inequality tells us that if you have two L2 functions, f and g, then the integral from 0 from of 2L2 function, the integral like this, is f times the g is the integral from 0 to 1 of f square dt times is less or equal to this one times the integral from 0 to 1 of g squared to the power 1 over 2, g squared to the power 1 over 2. That means here we have we have two functions also. Let me show you where they are. This is our fixed function that can be our g, and this is our second function that is our f. So we have two functions. We can see that this is an L2 function. Both of them are L2 function. But first, before we do that, let us remember that this function inside here is positive function. And since our x is in this interval, so the interval 0x is a part of the interval 0 to 1. Therefore, all this is less or equal to the integral from 0 to 1 of the absolute value of t, the absolute value of f of t, dt. So this function here is positive, and no, this is why I used it. Then from here we can see how to use this because we don't have the dependence on the boundary condition and in the boundary of the integral with on x. So we only have this number 1. So we can apply this order inequality directly together. This is going to be less or equal to the integral from 0 to 1 of t squared to the power 1 over 2 times, now here, the integral from 0 to 1 of f squared to the power 1 over 2. But remember, the integral of f squared to the power 1 over 2, this is equal to what? Let's see. This is exactly what we've called the L2 norm of f. So here we have the L2 norm of f, which appeared and this number we can compute it. It is going to give us 1 over, so square root of 3 over 3. So this is square root of 3 over 3. So this is our r, the r we were looking for. Therefore, we have found. Then we can take r to be square root of 3 over 3, which is positive, and see that what? See that this df of x is less than r L2 norm of f in L2 for all x in the interval 0, 1. Since this is the case, so if I take the soup which is the smallest, so this quantity is an upper bound of the set of df of x for x in the interval 0, 1. Therefore, the supremum of the set, which is the smallest upper bound, is always it is still going to be less than this upper bound. And when we remember well, we know that this is the C0 norm of our operator, less than R times the L2 norm of our F. This proves that your operator T is bounded. So we have solved this question. So we have solved this question first. This question is solved. So the first question is completely solved. So we have been able to find an R that is solving our problem. So now we have to go to the second one. The second question, we have to compute this operator norm, the operator norm of f. The operator norm is what? Is basically, it has a lot of definition. It is the supremum of the TF of C0, norm of C0 for f in L2 with norm less or equal to 1. You can also compute it as the sup of TF of C0 divided by the norm of L2 for all f non-zero. This is also equal to the sup of, it is known, of norm of TF in C0 for f, which is such that the L2 norm of f is 1. This is also equal to the infimum of numbers of the set of real number from 0 to real number, positive real number, let me say it like this, such that TF C0 is less than C F L2 for all F in L2. All these are definition of the operator now. So we will see which one is going to help us to get the solution. We first look at this. We first look at this definition here. This formula here. It is basically says that this is going. The operator norm is going to be First, let us look at this one. This equality. So the operator norm is going to be this infimum. So then it's going to be less than all the constants, real positive constant C, such that for all f in L2, you have that the C0 norm of TF is less than this C times the L2 norm of f. But we have seen here that this works for this square root of r, which is square root of 2 over 2. Then we can say that square root of 3 over 3, sorry. Because this square root of 3 over 3 is one of the elements that we can put here that satisfy this condition for all f in L2. Therefore, our operator norm, we already know that it is less or equal to this square root of 3 over 3, because it must be the infimum. The infimum is the lowest, the biggest yeah, the infimum is the lowest element. So it's like the smallest element of a set. It can be the smallest element of the set, the minimum if it belongs to the set. It can also be just a number that is very smaller than all the rest, but bigger than all the number that are smaller than the element of the set. So this, since this belongs to this one, it must be bigger than the infimum. Now let us see if we can reverse this inequality to get that actually the null is square root of 3 over 3 instead of being just less or equal. To reverse, we need the formulation of the operator norm where in terms of supremum, because we want it to be bigger. We want it to be bigger than something. So we have to, so we want it. So our aim is to show that we also have this one is bigger than square root of 3 over 3. So because we want it to be bigger, we have to look at the formulation of the operator norm in terms of supremum, because supremum will be bigger than element. So our effort is going to be to put this element, this number. So our effort is going to be to put square root of 3 over 3 as a member of so like a member of one of these sets. We can put it like here or there or there or there. For that, we need to think of a function. We need to think of a function that can help us to have it. We need to think of a function that can help us to have this number like this. That means I need to think of a function. I need to think of a function f such that if I compute tf like this, C0, I can get that this is equal to maybe square root of 3 over 3, or if I compute, so in the condition that the C0 of this one is less than 1, if I want to be here, if I want to be in this interval, in this set, or I want to think of a function f such that if I compute tf C0 divided by f like this in L2, I get square root of 3 over 3, where this f is not 0 if I want to be in this set, or I have to think of a function f if I want to be in the other set, which is such that if I compute this C0, I get square root of 3 over 3 when this f is such that its L2 norm is 1. So here you need to be careful and think wisely. So let us try. Pick f of t to be equal to t for all t in the interval 0, 1. Is this function an L2 function? Yes, it is an L2 function because it is continuous on the interval which is bounded, so it is an L2 function. Then f is an L2 function in the interval 0, 1. Now, let us see. Is this f such that is oh no, yeah, I should put L2 norm. Let us compute the L2 norm of f and see if it is less than 1 or it is equal to 1, but we know that it is not 0, so f is already like this. And let us compute first the L2 norm of f. So let us compute the L2 norm of f. The L2 norm of f is what? The integral from 0 to 1 of t squared to the power 1 over 2, right? What is this? This is going to be 1 over 3 to the power 1 over 2, which is square root of 3 over 3. But this quantity is less than equal to 1. It's totally even less than 1. Let me write it. It's totally less than 1. Therefore, our f is here. So now we will be done if we can prove that with that definition of f, if I compute the C0 norm of TF, I will get square root of 3 over 3. Let me see. Compute then the T0 norm of F. T0 norm. Which is this? What is this? Is the soup of what? Of this quantity. T, the integral of T F of X, and then with X in the interval 0, 1. But let us compute first of all Tf of X with this F. Tf of X is the integral from the absolute value from 0 to X of T, T times F of T dt in absolute value. This is going to give us the integral from 0 to X of T squared dt in absolute value. But T squared is positive, so the integral of a positive function is positive. The absolute value of the positive number is just the number in question. T squared dt. So what is this? This is going to give you x cubed over 3, right? This is going to give us s cubed over 3. And then we have, yes, s cubed over 3, right? So now, if one wants to know this TF of C0, which is the soup of then TF of X, like this, when X is in the interval 0, 1, this is going to give us something like the soup of x cubed over 3 with x in the interval 0, 1, right? So now let us see. What is the supremum of this one, this function? X cubed over 3 when x is in 0. Because this function is increasing on this interval, it is an increasing because, it is an increasing function. So the supremum, which is even the maximum here, is going to be 1 over 3. So we have a problem. You see that your TF didn't give you a square root of 3 over 3, but it gave 1 over 3. So we need to do something to solve this problem. What can we do? So with this f, we are not here, but we think that we can make this f belongs to this set. How can we do that? Then take just g, or let's just take f stars to be square root of 3 times this f of t that we have chosen. So we have square root of t, 3 times t. With this one, we know that tf stars now, which is then the C0 norm here, it is going to be t, it's going to be square root of 3 times what? Times t f, our old f. Why? Because t is linear, so if I put a constant like this, I will just put the constant outside of t. So, but we know by the property of norms that the norm of a scalar times a vector is just the absolute value of this one times t of f in C0, but the absolute value of square root of 3 is just square root of 3 because square root of 3 is positive. And this one, we have already computed it, we have obtained this one. But then you see we have square root of 3 over 3. But let us see what will be then the L2 norm of this f stars now. F stars being square root of 3 over f of t, like this. So this is going to be square root of 3 times the norm of our old f, L2 norm of our old f. But the L2 norm of our old f was square root of 3 over 3. This is 1. So this f stars, as we've chosen it, f stars is in L2, and the L2 norm of f stars is 1. Therefore, if I compute Tf stars C0 is an element of the set T, let me call here G, C0, where G is such that the L2 norm of G is 1. Therefore, this T F stars C0 must be less or equal to the supremum of this set, which is my operator norm, the operator norm of T. Therefore, square root of 3 over 3 also is less or equal to the operator norm of T. Then, at the end of the day, you have that the operator norm of T is exactly equal to square root of 3 over 3. And this solves the second part of the exercise. The third part of the exercise, 3, where now we have to show that our operator is actually a compact operator. So here we also need some definition of what we call compact operator before we proceed. A compact operator then is going to is an operator that maps any bounded transforms any bounded subset of the domain of its domain to a relatively compact a relatively compact subset of the the arrival space. So we have the compact set for all bounded subsets B of the domain. Let me write the DOM of T. This is what we call compact operator. So that what we're gonna do is we are going to give ourselves a bounded subset of the domain of T, and we're gonna show that the subset T of D is going to be relatively compact. So we let the domain of D be in the domain of T, which is L2 of 0, 1 of T, sorry, be bounded. We give ourselves a bounded. What does it mean? We have to write it somewhere here so that people will know. There is a constant that doesn't depend on any, that depend on your B. So there is a constant that we can call C of B greater than 0, such that for all F in B, you have that the L2 norm of F is less or equal to this CB. This is what it means that this B is bounded. Now we have to prove that T of B is relatively compact, is relatively compact in our arrival space, which is C0. So for a space, for a set like this to be compact or relatively compact, in C0 we have the Arzelà-Scully. I don't know how you write it. Scully theorem. Arzelà-Scully theorem. Let me find the correct spelling of. I'm not very strong, like maintaining the spelling of names. Arzelà-Scully. Yes, I wrote it Arzelà-Scully, so it is Arzelà as a Ascoli theorem. So I'm not very strong. I'm sorry for that. I'm not very strong on retaining like keeping. I used to say people's name everywhere. So then we have to show that by using Euler's theorem that T of B is uniformly bounded, and equicontinuous. Continuous. This is what we have to show for this TB to be relatively compact. Then we will go. So what does it mean? First, you need to know that T of B, what is it? It is the set of TF when F is in B. This is the direct image of B by T. Second, we need to show what does it mean uniformly bounded. We also need to show that there is a constant that we can call a constant K that only depends on B, then greater than 0, such that the C0 norm of TB, only the C0 norm of like this is less or equal to KB for all F in B. If we can find it, then we can conclude that our. So what does it mean? The second one is equicontinuous. What does it mean? Equicontinuous. For a family of function to be equicontinuous, it must be equicontinuous at every point of x, of the domain of the definition of the function. So we have to prove that for all x in the interval of 0, 1, TB, this set TB, which is the set of function, is equicontinuous at x. But then this brings us again to another question. What does it mean to be equicontinuous at a point? So TB being equicontinuous at a point here, it means that for all epsilon greater than 0, we can find a delta, a real number greater than 0. Let me write it as I like to write it. We can find a delta, a real number again, sweetly greater than 0, such that for all in other thing, W in the interval now here, 0, 1, if W minus X is strictly less than epsilon, then we have that the absolute value of TF of X minus TF of W is strictly less than epsilon for all F in B. For all F in B. So this is a little bit stronger than continuity. It means that all the functions are continuous on X at X. Sorry, but this constant, if it was like, for example, I was concerned about one function F, this constant delta here would depend on the F that I consider. For example, I will say that for all epsilon greater than 0, there exists a delta, but that delta will depend on this F. It will also depend on the X, because yeah. But here, the delta doesn't depend on F. Delta only depends on X, because in this way we have fixed X here, so delta here must depend on X. So this delta depends on X, but not on F in B. But look, this delta works with all the F that I can take in B. That's why the definition is a little bit stronger than the continuity. So yes, inside of this one, you have continuity. but it is more than continuity. It's very, very strong. So then we have to prove this one. First, let us see how we can have that this is true, how we can find this constant kb so it will be 0 so that this is true. For that, we have to compute the C0 norm of TF for any f in B and see if we can identify this constant. If you compute the TF C0 norm of TF, we know that this is square root of 3 over 3. The L2 norm of this one from what we have computed before for all f. But here f is in B and B is uniformly bounded, and for that in this way we know that there is a CB. So there is a CB such that this is less or equal to square root of 3 over 3 times our C that depends on B. So this will be our KB. So we have identified our KB, which is said that this is for all f in B. For all f in B. Because of the boundedness of B, so this CB exists and it satisfies this property, the property that we have written here is satisfied this property. Therefore, we can apply it to compute our KB. So we have proven that there is a KB, right, defined as square root of 3 over 3 times CB, which is positive because CB is positive and this is also positive, which is that the C0 norm of TF is less or equal to KB for all f in B. So our TF is uniformly bounded according to what we've presented here. Now we have to show that this B is also equicontinuous at any x, so let us fix. Let now x be an element of the interval 0, 1. So we have fixed this one. We have now to show that if we pick any epsilon positive like this, we can always find a delta that will depend on x and all those things. But for that, let us, for all epsilon positive in the set of real number, we must first estimate this quantity and see how it behaves. And then after that, we will see how to identify this delta that will depend on x, only on x. So let our compute TF of x minus TF of w for all f and for all f. So what is this going to give us? This is going to give us the integral from 0 to x of TF of t minus the integral from 0 to w t f of t, right? But then this can be written as the absolute value of the integral from x to w. Let me write a plus or minus here because it depends. X can be bigger than w or w can be bigger than x. So in any case, we are going to have something here with a minus or a plus sign before, which will disappear at the end of the day. So later, just write it to precise that we don't know which one of x and omega is bigger than the other one. Then with this one, what we're gonna do is you're gonna look at this. What's gonna happen here? We can use again the fact that this function, the interval xw or wx will all be part of the interval 0, 1. So now, since our TF, t times f is integrable, t is L2 in, so the function t is L2 in 0, 1. F is L2 in this one, it is also L2 there, right? So now what we can do is we can use then the Euler inequality here to get this is gonna be less than integral from x to 0 w of t squared 1 over 2, and this is the integral from x to w of f squared of t. I keep the absolute value to say that I don't know which one is minus or plus here. But in the first case, we see that this is going to give us x cube over, so in absolute value, s cube over 3 minus w cube over 3 in absolute value to the power 1 over 2, right? Times here, what are we going to have? We are going to have something like the integral from x to w in absolute value of f squared of t 1 over 2. So this is going to be less or equal to that over x squared over 3 minus so we can put 1 over 3 outside. Let us put 1 over 3 outside. We have here 1 over 3 times x, or so the absolute value of x minus w times x squared plus xw plus w squared in absolute value. Let me write it here. In absolute value 1 over 2. And here it's going to give us the L2 norm of, it's going to be less than or equal to the, why? Because the interval x to w or w to x is going to be a part of the interval 0, 1. So the integral of f squared on this interval is going to be less than the interval of f squared on the interval 0, 1, which will give us the L2 norm of the interval 0, 1. The L2 norm of f in the interval 0, 1. But then here we can see that this quantity is going to be x squared is going to be less than 1. This is less than 1. This is less than 1. So the product is going to be less than 1. This is also less than 1. So the square is going to be less than 1. So all this is going to be less than square root of 3. So this is less than square root of 3 over 3 times x minus w times f in L2. But we must remember that our f is in B. So all this quantity is less than CB. So we have CB times square root of 3 over 3 all times x minus w. So we have that. What can we conclude? For all x and for all w, sorry, I don't need this one. Yes, for all f in a B, well, one hand, and for all w in the interval 0, 1, one had that tf, the absolute value of tf of x minus tf of w is less or equal to this CB, the constant that we've identified, square root of 3 over 3, and the x minus w, right? So now, if we x minus w is strictly less than epsilon over 1 plus CB minus square root of 3 over 3, what is going to happen? So this is our delta. You can define delta to be equal to this one. So here delta doesn't depend on x, which is very nice. This is our delta. What is going to happen? We're gonna see that TF of x minus TF of w, which will be less than CB times square root of 3 over 3 times this quantity is going to be less than epsilon over 1 plus CB times square root of 3 over 3. But this quantity is equal to what? Epsilon times CB times square root of 3 over 3 divided by 1 plus CB times square root of 3 over 3. But look, CB over 1 plus CB square root of 3 over 3 is strictly less than 1. So this is strictly less than 1 times epsilon, which is epsilon. So what have we proved? We have proved that for all x and for all epsilon greater than 0, there is a delta. It depends on x, but here it didn't depend on x, so that we have defined in this 4 CB square root of 3 over 3. Sorry. It is defined in this form, epsilon divided by 1 plus CB times square root of 3 over 3. Greater than 0, such that for all W in the interval 0, 1, X minus W still less than epsilon implies that TF of X minus TF of W is still less than epsilon for all F in B. Therefore, T of B is equicontinuous. Equicontinuous at X 10 on the interval 0, 1. So we're having these two conditions together. One easily conclude that our operator is a compact operator. This is where the video ends. Thank you very much for watching. I know that this video was very long. Maybe it's because I was very detailed. I wanted to give all the detail, and I'm sorry for that. Thank you very much. Bye. And Mbote Lokuten Balasima pour les Congolais qui ont aussi suivi cette vidéo. Oyo Lingala Lokuten Balasima ou place à représenter un peu la matière dans la Bissonanga.